Hello, I am Zhao Gan, an instructor in the Huawei Talent Ecosystem Development Department, specializing in artificial intelligence. In the previous video, we learned what an optimizer is, the characteristics of each optimizer, and the common types of optimizers we often use. In this section, we will focus on explaining the types of neural networks. Before neural networks, we have talked about feedforward neural networks. So, in the important network of the feedforward neural network, how does the fully connected layer network develop behind it? Today, we will explain to you several important neural networks. The first one is called the activation neural network. Activate the neural network, which is a feedforward neural network, whose neurons can respond to a part of the surrounding units within a coverage area, making it excellent for image processing. Its structure includes convolution, pooling, and fully connected layers. So, how exactly did this convolutional neural network come about? Because of deep learning, it's actually a form of bionics, which I believe everyone should know. In the 1960s, when Hubel and Wiesel were studying neurons in the cat's visual cortex that are used for local sensitivity and direction selection, they discovered a unique network structure that could effectively reduce the complexity of feedback neural networks. Subsequently, it proposed the convolutional neural network, which was thus born. Convolutional neural networks are a hot topic in many research fields and are currently widely used in pattern recognition and classification. They can avoid complex preprocessing of images and directly input raw images, which is why they have gained extensive applications. With such a basic background knowledge, let's re-examine the structure of convolutional neural network. We know that the proposal of convolutional neural networks is based on some neurons in the cat's visual cortex that are sensitive to local patterns and orientations, and then a neural network is proposed with what characteristics. So, from this feature we can identify its core idea. First, let's look at the first feature, local perception. Because human understanding of the external world is a state from local to global, that is to say the spatial connection of our image is based on local pixel connections, which are quite close, while the correlation of pixels far apart is relatively weak. Based on this, our network presents a convolutional state, which means it is a local perception state. In other words, the first hidden layer only connects to the first point of the next layer, possibly locally connected, without achieving full connectivity. This is a structural characteristic of it. Then let's look at our parameter sharing. What does that mean? It means that when we are doing convolution, there is a convolution kernel or multiple convolution kernels scanning this image, scanning a pixel value of this image. Each convolutional kernel comes with its own parameters, which are the weights. Among these weights, when it traverses, the parameters it uses remain fixed, thus achieving parameter sharing. So, based on these 2 points, we can understand the core idea of convolutional neural networks well. Let's take a look at the general architecture of convolutional neural networks. First of all, it has our convolutional layer, which contains our convolutional kernel that performs convolution computation. Next, we have the pooling layer. The pooling layer employs various pooling methods, and finally, we have the fully connected layer which outputs the probabilities for multi-class classification, determining the class to output. This is an example of bird image classification, which means that when we learn if this image is a colorful bird picture, along with birds, sunsets, dogs and cats. Okay, for our color image it has 3 channels of RGB. Then, for these 3 channels, we perform the same convolution calculations sequentially. After convolution, the output goes to the next layer, which is the pooling layer using max pooling to obtain a smaller image. When we look at it after pooling, the image size has decreased. Why does it shrink? With these questions in mind, let's first understand how to perform convolution calculations. First, let's take a look at it having a 3x3 convolutional kernel. How does it perform convolution with a 3x3 convolutional kernel? The first step we take is to match the size of our original image. Here, we use a 3x3 convolutional kernel to match. The first step is to start from the top left corner, then match and calculate a value. How to calculate? It's by multiplying at the same position and then accumulating the sum. Okay, let's take a look. This value contains ones at diagonal positions. At diagonal positions, there are a total of 5 values. In other words, in this one, it is 0, so when multiplied, it will definitely be 0. This means that after multiplying and adding the very first value, its value is 4. We move in order, first from the left, then to the right. During the movement, we need to consider the stride of the movement. If the stride is 1, it means that the next time we calculate, we need to match this small window. After calculating from left to right like this, then calculate from top to bottom. Let's take a look at a rough process of our convolution calculation. First, it performs the first calculation from left to right, then sequentially from top to bottom, with a certain stride from left to right. From left to right, everyone take a look. There is a stride of 1 horizontally, and also a stride vertically, which is 1. You can set a different stride. Here, we are dealing with a calculation, that is when our output value outputs an image size of W multiplied by W. Our feature is the product of F and F in this way, then for the stride we use S to calculate it, and our padding is done with P. What does padding mean? For example, if our stride is 2, the first step is like this, and the second step is here. Is the third step here. If we don't add padding to this part will not perform convolution calculation. If padding is added, by adding a column or a row, we can continue with the next part of convolution calculation as a supplement. This is the role of padding, preserving edge information. For B, what size can we get after a convolution? The calculation method is to subtract the size of the convolution kernel from W. Add twice the padding size, padding is added on both sides or top and bottom, then divide by the stride and add 1. This result is the size of our image after convolution. Everyone can use this method to calculate the size of our image after convolution. Okay, after completing the convolution calculation, let's take a look at the workflow of the convolutional layer. First, we import our output tensor, then perform convolution. After convolution, this part is the product. Then add our bias. This part is equivalent to performing a linear function. After obtaining the result from this block, we then input it into our activation function, perform nonlinear transformation, and after the nonlinear transformation, this result is then output to the next layer. This is the workflow of our convolutional layer. After understanding the working principle of the convolutional layer, let's take a look at the pooling layer next. Our pooling layer also moves with a local window 1 by 1. First, we need to select a size for pooling, a dimension for pooling, and then proceed from left to right, and then from top to bottom, also involving the issue of stride. There are 2 pooling methods, one is maximum, and the other is average. Let's take a look at the maximum pooling and how it performs pooling. First, select a 2 by 2 area, then choose the maximum value 56 in this 2 by 2 area as a representative value, then move with a step size of 2 to the next step, which is 48, then continue downwards with a step size of 2, selecting 255 and 32 in order. In this way, we can complete a pooling step. After pooling, we can see that the size of our lower level input has been reduced, achieving a dimensionality reduction effect. Therefore, our pooling layer can also be considered as a certain selection of features to some extent. Okay, we'll stop here. Let's supplement everyone on when to use max pooling and when to use average pooling. Our results and errors are caused by 2 parts, one of which is the size of the local neighborhood. The errors generated within our convolutional layer will lead to deviations in the estimated values and their average. Okay, so our average pooling can address the first issue by retaining some background information. On the other hand, our max pooling can alleviate errors in our convolutional layers and focus more on the textures in the images. So, these 2 points, everyone can go and focus on understanding. This is our pooling layer. Let's take a look at the fully connected layer. In fact, when we explain the activation function SOMFEX, we explain it, that is, for multi-classification. Then we need to take the score, the probability of each class, and use this function to calculate it. In order to output our final model, what category does it belong to? This is convolutional neural network. After convolutional neural network, there is another one, recurrent neural network. Why do we introduce recurrent neural network? Due to recurrent neural networks, he is good at capturing sequential information, this dynamic information, because our CNN convolutional neural network cannot utilize context or a certain time sequence. A paper presents a result. For example, in the past, when we identified bird images, if it's a video, it consists of frames. If in one frame, this bird it made its wings disappear, it mutated and then it underwent a mutation, transforming into another type of bird. So for the final image, we cannot identify it based on the characteristics of the bird. Therefore, we need to understand what happens in between in order to determine the specific bird in the final image. This way, our RNN can capture the continuous changes and information. Just now, what I explained to everyone is an application in our video which actually involves sequences and continuous related scenarios. RNN can be widely and effectively applied, such as in audio, such as in our text. Let's take a look at how recurrent neural networks have been improved on CNN. They have actually added a memory unit, which takes our previous information, multiplies it by a weight, adds the current information, and then calculates it using a After expanding this memory unit, let's take a look. It actually represents this kind of computational process, which means that at ST1, we multiply it by a weight, then after the multiplication, ST1 is calculated. We can output the retained ST1, or input it to the next. Then, ST also utilizes the information from ST1 to integrate with the current information of U and XT. Calculate ST accordingly, and output it at time t. This output needs to be further transmitted to ST to provide it with a computing component. Here we see that for each W, so is W the same here. Here I tell everyone, in the memory unit we use the same W, the same weight, that is to say in this area we hear again, weight sharing. In the previous discussion, whether it was about weight sharing or when we used convolutional kernels, this time we mentioned another concept of weight sharing. This is an architecture of recurrent neural network. Let's take a look at what types of recurrent neural networks exist, and how many types there are. His network types include one-to-one, one-to-many, many-to-one, as well as many-to-many and many-to-many straight. Okay, these several types, that is to say in total there are 5 types. You can combine them in one-to-many, one-to-one, many-to-many, many-to-many. There are 2 types. Everyone should remember this lesson, so in total there are 5 types. Let's take a look at how he does backpropagation through time. We know that convolutional neural networks only need to do backpropagation, but how about time sequences? That is to say, how do you do it in your memory unit? Actually, it's quite simple. In other words, at time t, the gradient you calculate is actually the accumulation of all gradients from time 1 to t. As time goes by, the more information you retain, the more accumulated gradients you calculate, and the more apparent the disappearance of this gradient becomes. We summarized a 3-step process of reverse sequence backpropagation. First, calculate the output value, then compute the error value backward, and finally calculate our weight gradient. When calculating this error, we also need to consider some information and gradients from the previous T1 time step, and ultimately update our weights. As we just mentioned and also discovered the vanishing gradient issue, how do we solve? If you are already using the radioactivation function but still encounter the vanishing gradient problem during backpropagation, then we must modify our model. What should we use? With LSTM we just discovered an issue with our recurrent neural network. What is the problem? It has an issue of vanishing gradients. What other problems does it have? Let's take a look at the standard RNN. It solves the issue of information retention, but for long-term memory it decays. In other words, these long-term memories information could be crucial information, so this aspect will affect our outcome. For example, if we want to retain long-term memory information, such as in reasoning novels, at the beginning clues were laid out, and only at the end was an answer provided. Therefore, do we need the setup from the beginning to set off the conclusion? What do we hope for in this aspect at the end? It can remember key information rather than just the most recent information. We remember and compare information over a longer period, leading to forgetting. Based on these issues, we optimized by selectively choosing and addressing some information. To tackle the vanishing gradient problem, we used long short-term memory networks. Also known as the LSTM algorithm, it is actually a translation process. Let's take a look at this memory unit. This HT is the memory unit at time t. At this moment, our output input vector is X. In the previous moment, its algorithm in this area is HT1. As we mentioned before, ST1, the output, is HT1. Alright, how does this ST1 get transmitted into this unit, and then how is it calculated? We have seen many sigmoid functions and tan functions. These sigmoid functions actually act as gates. It is doing a gate operation, which means allowing some information to enter, then flowing to the next step for further computation, while excluding other information from entering. This effectively addresses the gradient vanishing issue in our recurrent neural network. Let's look at another optimized long short-term memory LSTM network. Since our LSTM network involves a large amount of computation and many functions, how can we address this? We can reduce the computation load and consider faster ways to obtain our answers. So we have corrected some gated recurrent unit, which is the GRU algorithm. In fact, GRU is a variant of LSTM, which means that the two gates we had before, one for forgetting and one for input, have been combined into one update gate. It means that our previous 3 subfunctions have been reduced to 2 subfunctions, making it simpler than the LSTM model. GRU was proposed in 2014, so when was LSTM proposed? It was proposed they all propose solutions to the same problem, which is addressing the gradient vanishing issue in the recurrent neural network, RNN. Here I will briefly explain the core idea of our GRU and LSTM, which involves incorporating a few functions here. Its specific computation process, we can all take a look at it in detail after class, to see how each layer is calculated. It's actually not difficult, just follow our direction and then calculate the output step by step. As mentioned earlier, it lacks a gate, compared to our LSTM, which means it has fewer parameters. Therefore its computation load is significantly reduced, ensuring a lower time cost for us. So in our engineering work, we generally use GRU. This is our recurrent neural network. Now let's take a look at another type of network, which is called a generative adversarial network, GRN. What problem does the GRN aim to solve? We want the generative adversarial network to generate images, generate semantics, do text generation, data generation, chatbots, information retrieval, sorting and so on. So we invented this generative adversarial network under such an, it's not specific but an optimization of previous networks. It's actually an idea, an architecture. In other words, I can achieve it through an adversarial form. In other words, how do I pit 2 CNNs or 2 RNNs against each other? What we do is to use a type of network, a neural network, as a generator, to generate a sample, then you have a discriminator to distinguish the difference between you and this real sample. If my discriminator fails to discriminate, it means that the sample generated by your generator is okay, and we can then apply it to text, semantics, images, and a generation scenario. Here let's take a closer look at what data the generator uses. In fact, it's just a noise, if noise. This noise follows a prior probability distribution selected by humans, that is, uniform distribution and Gaussian distribution. This generator adopts a multi-layer perceptron network structure and uses the parameters of maximum likelihood estimation to represent differentiable mappings, mapping the input space to our sample space. Then this generator can generate pseudo-samples. What does the discriminator do now? The discriminator assesses the similarity between your fake sample and your real sample. If the difference between the two is significant, it will determine that the sample is fake, meaning it is not genuine. If the generated one is similar to the real one, then you are. So the basic principle of our generative adversarial network is also like this. Combining this structure, let me explain the core idea to everyone. Take a look. This is an image with noise, then after some manual selection of data distribution, it is imported into your generator networks, which is our Through this generator, I generated a wonderful image of this kind, a Hello Kitty, and then with this Hello Kitty, both me and my real self, as input data simultaneously, input into the vector, import into our discriminator. Such a discriminator. If my discriminator judges yours to be genuine, then it proves that our overall cooperation is very pleasant between our generator and our discriminator. So we have met the requirements for our application and can proceed with the application. Let's take a closer look at our generative model, which is the Gaussian white noise vector mentioned earlier, and the output is our sample data vector. This means that through this type of network, you can sometimes use CNN or RNN. When dealing with different problems, you also use different methods. Here, what does our discriminative network do? The discriminative network actually takes as input your real sample and the sample you generate. Just now when we were explaining the concept of the discriminative network, we also explained to everyone that it outputs a degree of truth or falsity. Now let's take a look at what its training rules are like. Let's imagine, if we want to improve the overall performance of this model, what do we need first? We need to have a good discriminator, right? We also need a good referee. If the referee's standards are not very good, if your discriminatory ability is not very strong, then even if I generate a fake image, with images that have a big gap from reality, you actually judged them as real. Isn't that a joke? So our first step is to maximize D, that is to let it identify to the greatest extent what? To distinguish between our generated samples and our real sample. Then our generative model minimizes the gap between the two, forming our value function, which is the training rule of the generative adversarial network. In this section we mainly talked about different types of neural networks: convolutional neural networks, recurrent neural networks, and generative adversarial networks. In this section we have come to the end. In the next video section, I will explain to you what kind of problems we often encounter when working on deep learning projects, and how we can solve them. Thank you for studying and watching this video section. See you in the next section. Good.